What's up, guys? It's Chris coming at you with another helpful tip. And today we're gonna be discussing something I like to call the 30 60 90 triangle. And it's a difficult concept even for those smarties out there. But I'm gonna break it down for you real quick and make it easy, simple, and just generally, let's have some fun with it, guys. Come on. Guys, it's Chris. We're gonna be teaching you how to decipher a 30 60 90 triangle today, and what does it mean, how do you apply it, and just generally, what is a 30 60 90 triangle? So let's start. So the basis of all triangles is an equilateral one, and triangle has 180 degrees in it. So by equilateral, each side or each angle is 60 degrees. So they all have equal angles. Because they have equal angles, this means that all of the sides are going to be equal as well. All of the sides are going to be congruent. So I'm just going to assign each side a number right now. You can assign it really any number, but in this scenario, I'm going to assign it 2. So each side is going to be 2. Now, to get a 30 60 90 triangle, what you want to do is you want to split this triangle in half. Now, what that does is give you two separate right triangles, which is a triangle with a 90-degree angle. And when you cut the triangle in half up here, you also cut the angle in half. So half of 60 is 30, so you get 30 degrees here and 30 degrees here. Now, when you cut this side in half, that cuts the 2 in half as well. So you have one side here, or one here and one here. So to make it a little easier on the eyes, you can kind of remove these two right triangles from the greater equilateral triangle and just draw them as what they are, which is right triangles down here. Gotta know the angles. You just got it. So here we go here. And as I said before, we have a hypotenuse of 2 and a leg of 1. And we'll do the same over here. And the only thing you don't know is the side opposite the 60-degree angle. So I'm going to refer to my good friend Pythagorean theorem, which if you study anything at this school, you know it's a squared plus b squared equals c squared, which is c squared is the hypotenuse, and then these two are the sides, so the leg and the height. And so we know one leg, which is 1 squared. We don't know the height yet, so that's just going to be b squared. However, we do know the hypotenuse, so that's going to be 2 squared. Then you just solve. Simple as that. 1 plus b squared equals 4. I just did some simple math in my head, but 2 squared equals 4 and 1 squared equals 1. So you just use simple algebra to find b squared here. You subtract 1 from here, subtract 1 from here, and you're left with b squared equals 3. But you thought it was over. No siree. You got to take the root of this bad boy, because b squared cannot be left as b squared. You got to get that value down to the original. So we're gonna root 3 as well. So we're gonna end up with b equals root 3, and that is the answer to that side. Math Nation. So right now we're gonna be going into the famous 30 60 90 chart. So this chart is it's really special because you can plug in x for any of these values. And if you do it orderly, if you plug in 2 for x here, then you get every single value for the side that corresponds with this angle. So I'll do some examples right now. So let's say the side opposite 30 is I don't know, 2, whatever. This is 2 right here. The side opposite 60, 2 root 3. That means the side opposite 90, 2x, 4. Let's plug that into Pythagorean theorem, why don't we? 2 root 3 squared plus 2 squared equals, it should equal 4 squared. Let's check to see if we're right. So, root 3 squared is 3, 2 squared is 4, so 4 times 3 is 12, plus 2 squared, which is 4, which equals 16, which is 4 squared. It's not a coincidence. So I'm going to be doing a tutorial on the 45, 45, 90 triangle. And this may blow your minds, but we're going to start out with a square first, which is not a triangle, but I'll show you guys a little something about math I like to call transformation. And so we all know that squares have they're all composed of completely right angles. So, you know, they have right angle here, right angle here, right angle here, and right angle here. And another thing that squares have is completely congruent sides. They're all the same. No matter how you slice it, squares have equal angles and equal sides. That's interesting. Let's cut it in half, why don't we? What happens here is, we get a special kind of triangle, and that's called an isosceles. That's when we have 2 equal sides. I'm just giving the 2 equal sides the category of 1, but you can really choose any number. And since you're slicing the square directly in half, you're gonna get some peculiar angles. Obviously, you have the right angle placed right here, but you're also gonna get a 45 angle here because you cut a 90-degree angle in half. You're gonna get a 45 over here as well. These are 2 triangles. And then right here, you're gonna get a 45 as well because what did you do over here? You cut another 90-degree angle in half. That's what you did. So this is a 45, 45, 90 triangle. And to make it a little simpler for the weak eyes of the populace, I can draw it outside of the circle. And that's gonna look a little bit like this. These are 1s, by the way. And you know everything in these 45, 90 triangle, except one thing, and that's the side opposite the 90-degree angle. And how do you think you get that? Boom! Pythagorean theorem. This is a squared, b squared. 1 squared plus 1 squared equals c squared. It's 1 plus 1 equals c squared. So I guess that means 2 equals c squared. And when you have a squared and you want to get the number you want to get the exponent by itself, you root it. So c ends up being root 2. That's funny. So 45, wow, a 40, I can't even do it. I can't even do this. So guys, now you learned what a 45, 45, 90 triangle is, and now you're gonna learn how to get there the simplest way. Here's what I like to call a chart. Shows you, what you need to plug in to get the corresponding side lengths of a 45, 45, 90 triangle. And I'm not even going to bother explaining this one because it's so simple, a small child could do it. But if you want, you can just plug in some random whole number for x, x equals 3, x equals 4, whatever. And you can do that, and you will find the corresponding sides easily, I guarantee you.
That girl, no matter what you say, marry that girl, we be a family. Why you gotta be so rude?
Why do the signs of the sine and cosine functions of angles in standard position vary depending on the quadrant in which the angle has its terminal side?
The signs of the sine and cosine functions of angles in standard position vary depending on the quadrant it's in and in which quadrant their terminal side is in. So if we have a 30, 60, 90 triangle in quadrant 1. The x is in the positive direction. It's going in the positive way. So the x equals positive. The y-axis is also going up in quadrant 1. So the y equals positive. And by this logic, if the x is positive, then the adjacent, which is the segment of the x on the triangle, will be positive as well. And that also goes to say that if the adjacent on this side, if the x is negative on this side, then the adjacent will be negative. And if the y-axis is positive, then the opposite will be positive. And as well on the other side. So if the y is negative, then the opposite will be negative. And so if you look at the second quadrant and you make a 30, 60, 90, you realize that the x is negative. It's going in the negative direction. However, the y is still positive, and the hypotenuse is positive, just it's always positive. But by this determination, you don't even really need to know the side lengths. You can determine that if sine theta equals opposite over hypotenuse, and you know that the y is the opposite, you can determine that positive over positive means that sine theta in this quadrant is going to be positive. Now if you do tan theta, that's where it starts getting a little tricky, because it's going to be opposite over adjacent. And the opposite, as we know, is positive. However, the adjacent is negative because it's in the negative x direction. So you're going to have, for tan theta, you're going to have the opposite, which is a positive, over the adjacent, which is a negative. So it's going to be negative. For the cosine, you are going to have the adjacent, which is negative, over the hypotenuse, which is positive, again having a negative cosine. So now on to quadrant 3 and quadrant 4. So you see in this one that the x value is moving in the negative direction, as well as the y value, because it's going down. It's going down the y-axis. So, and we all know that the hypotenuse is positive constantly. So if the x is negative, that means the adjacent's negative. And if the y is negative, that means the opposite's negative. So when you do the math, tan theta, which is opposite over adjacent, means that the opposite over the adjacent, the negative over the negative, makes a positive. So the tan is positive. I'll just write that down here. So the tan is positive, and if you do sine theta, it's opposite over hypotenuse. And the opposite, which is y, in the y value, it's going to be negative. So it's negative over plus, because the hypotenuse is always positive, which equals negative. And finally, for cosine, you know that the adjacent right here is negative, so it'd be negative over the hypotenuse, because cosine theta is adjacent over hypotenuse, which is positive, so the cosine would be negative as well. So now you have the tan is plus, the tan is positive, the sine is negative, and the cosine is negative. Finally, for the quadrant 4, the most challenging quadrant, you know that the adjacent is positive because it goes in the positive x direction. However, the y is negative, so because it's going in the negative y direction. The hypotenuse is always plus, is always positive. So when you do tan theta, opposite over adjacent, you're going to realize that negative, opposite is negative, and the adjacent is positive. So it's going to be a negative over a positive, making it a negative tangent. And sine theta, which is opposite over hypotenuse, is negative, which is opposite, and the hypotenuse, which is plus. So you're going to have negative over positive, resulting in another negative. So, sorry, it's going to be a negative sign. Finally, for cosine, cosine theta equals adjacent over hypotenuse. You know the adjacent is positive and the hypotenuse is always positive, so it's going to be a positive over a positive, meaning that the cosine of quadrant 4 is always positive.
Dang, after learning all this knowledge, how does it relate to the unit circle? Wish I knew.
Alright, what's up guys? I'm going to be teaching you how to do a little something called the unit circle. It's, I'm going to show you how to get the points, the designated points right here by knowing the angles and the sine and cosine of them. So this is a true statement right here. It's root 3 over 2 1/2 equals cosine theta sine theta, and this is for the 30-degree angle in the unit circle. And in the unit circle, all the hypotenuse or the radius are 1 because it's one unit. It's a unit circle. So to find the points of this value right here, you're going to want to make this a triangle so it's easier to kind of figure out what you're doing. So in 30, 60, 90 triangles, you have an x and a x root 3. Now in this case, the hypotenuse is going to be 2x, so we're going to have x over 2 and x root 3 over 2. And now, here's where the real fun starts. If you plug them into cosine, that equals adjacent over hypotenuse. If you look at it, the adjacent is x root 3 over 2, and the hypotenuse is 1. So it's going to be x root 3 over 2 over 1, which is just, so any number divided by 1 is just going to be the number on top. So you get root 3 over 2, which is, boom, that's what's given to you. Then let's try sine theta. That's opposite over hypotenuse. If you look at the opposite, you'll see that the opposite is x over 2, or I mean, now that we have our value, it can just be 1/2. So sine theta equals 1/2 over 1. Again, whenever you divide by 1, just makes it the number on top, so you're going to be left with 1/2, which is the point here. That's pretty peculiar. So when you do the cosine and the sine of a triangle, the answers to that are the x and y value. And this is because the cosine of theta equals, it's adjacent over hypotenuse, but the adjacent, if you can see, is the x, so x, and the hypotenuse is just 1. And any number over 1 is just going to be the number that it's originally supposed to be, so x. That means that cosine equals x. And for sine theta, that's opposite over hypotenuse. If you look, the opposite is the y value. So it's going to be y over hypotenuse, which is always 1. And that's just going to be y. So sine theta equals y. And that's why you can determine the coordinates of a point based on cosine theta and sine theta. And you can do the same process for 45 degrees, 60 degrees, and
You can't get mad, I'm only getting started. I won't